Hello, everyone. Good morning.
Good morning.
Yeah, morning. Happy Friday. Okay. Yeah, Friday. So I don't see many people here, but let's waste some time. Yeah. Before that, I want to say something. For the assignment 3, I noticed that TA told me that some student didn't finish the multi-threading, maybe because you forget about that, or maybe because of not working. Anyway, I don't think that's a problem. We can ask a TA to do a demonstration lecture. Okay. So yeah, good note. Yeah, only cookies here. Yeah. So I believe if you are here, so you can get a very good grade finally, right? Okay. So anyway, I mean, for multi-threading class, the assignment, I can ask TA to give you a demonstration, sometimes next week, right? So, if you don't know how to do that, but I think that's useful. Okay. So anyway, I don't think that's a big deal. I told TA that that question is only about 15 scores credits. Okay, so that's fine. But hopefully you can know how to do that. But just 15 scores. If you do something, definitely that would be great. But not, don't worry. Okay. I can hear him loud and clear. Okay. Any problem with my voice or sound? Because I'm using a headset. Not sure if it's working or not. First time using this. If my voice or sound has some problem, let me know. Okay. Okay. So let's continue with the lecture. Let me share my screen. Okay, so I think last lecture we were talking about IP, right? How addressing, and we ended up in a network address translation. Let me quickly go through that again with some more details. So the idea is that we have some local network, right? But if you want to see the outside world, you have to let the outside world know um, how to address you, right? What's your, but you only have some local IP within the local network, right? How we can do that? So the idea is that once you your datagram sent from the router needs to translate your local IP, right, local address to something global, globally can be read, right? So here is all devices in local network share just one IPv4 address as far as outside world is connected. As we mentioned, there is some uh, good thing here, right? The benefits here, right? So here is a diagram, right? So when you send the, let me change the laser point. When you send something from the local network to the rest of the internet, right? You have to translate, your address need to be translated here. And every device within the local network will use the same global IPv4 or global IP address here, okay? And I think the benefit is that uh, all of the local devices only share one IP address. No matter how you configure your local network, you don't need to change the global address, right? Just as I mentioned in last lecture, right? So if you are, all of them are Washington State University students, so we are share the same WSU name, right? People want to find you, just come to the WSU, and no matter how you change your ID within the university, that's fine, okay? And you can change ISP without changing the address of device in local network, and also some security benefit here, okay? So let's try to give some more detail about how we implement that. And the NAT router must to be transparent, because as a device, you don't want to handle this, right? The translation should be happened in transparency. Okay, so outgoing datagrams, how should we do? We need to replace the source IP address, port number of every outgoing datagram to network address translated IP address and the new network port number. The remote client servers will respond using the NAT IP address, new port number as a destination address. So remember every source IP address and port number to translate to NAT IP address and new port number translation pair. Okay, whatever. I think I will show that animation here that would be easy for you to understand. So let's say if I have some packet, right, datagrams need to be sent to the outside world, right, to the internet. So the host, first this host, right, we have the host 1, 2, 3. Still remember the subnet, right? So this is, for example, this is a subnet mask with 24. So the last 8 digit, we can have a 255 or 54 devices here, right? So for example, we have 3 devices in the subnetting network. And the first one needs to send the datagram to, this is the global IP address. Okay, this is the global IP address and with the port number 80. So you can see here the source, the destination, sorry, the source IP is your local IP, right? Before translation, okay? It's a local IP with your port number and destination IP address with the port number, okay? The global IP address you need to send to, okay? And then after you pass the router, so the router needs to translate your local IP address to some global IP address, right? So you can see here, because the this router IP address, you can translate into the 138.76.29.7, right? With the port number. This is something you have been translated to, okay? With the new port number, with the IP address of the router. Okay, and you keep the same destination IP here. So you can see the first step is the NAT router changes datagram source address from the local address to the global address based on the translation table. Okay, and once the, for example, if you are doing something with the HTTP and the server will reply something, right? So the reply something to the, you can see here, the destination is what you have been translated, right? And this is a source IP address you have been sent to, okay? And reply that, pass the router, and the router will be translated the IP address back. Okay, for example, here we translate the 138.76.29.7 to the local one, 10.0.0.1 with the changed port number. Okay, this is just like a translation. Okay, it's not too complicated, but I want to go through that process. And you can see all of the local devices will share the same IP address here, right? After the translation. Okay, so you can see here, so NAT network address translation has been controversial. The routers should only process up to layer 3, and the address shortage should be solved by IPv4. Okay, here are some notes, but I think that should be fine. Okay, so you can see as here, NAT is here to stay extensive use in home and institutional nets, 4G and 5G cellular nets, because you will have some local networks and you need to translate it, right? So if if you are not within a home, if you are sitting in a very public area, maybe this is not working, but anyway, I think this is the important procedure to understand, okay? So I think next topic is about IPv6. Some of you may know that IPv4 and IPv6 different network, but some of you may not hear about that before. I think the motivation for the IPv6 is straightforward. Okay, the idea is that if we cannot have enough IP addresses with a 32-bit for the IPv4, how should we do? That's just a direct motivation. Okay, so the direct idea is that the straightforward idea that if you don't have enough bits for IPv4, definitely you should extend the bit number, right? 32 bits is not, enough. Then how should we do? Just increase to 64 or to 128, right? For the IPv4 case, we increase the 22-bit address to the 128. Okay, let's see some more details here. Anyway, so the initial motivation is the 32-bit IPv4 address space will not be completely allocated. It's not enough, right? Based on maybe in the 10 years or 20 years, that's not enough, right? Based on the speed is too fast increasing. So an additional motivation here is the speed processing forwarding 40 bytes fixed length header. So it's also because of the speed and enable different network layer treatment of flows, but blah, 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 that's whatever. But the basic motivation is we need to have more addresses for the internet for the devices. And I think interestingly, when you take a look at the previously computer system or architecture, when the first computer invented, I think that's only about some, if I remember correctly, it's some kinds of kilobytes, right, for the memory, because that time people could not think about, okay, in the future we can have a so powerful computer, and they just design several KB memory. They think that would be enough, but eventually that's not enough. That's totally not enough, right? So that's why we increase the memory. Maybe you think about some hundreds of gigabytes is pretty enough now, right, for your local computer. But in the future, that could be far away from enough. That's why I think people now are discussing the post-Moore law, right? So because the processor, the memory development have been, stuck because of some physical limitation, right? Because the transistors space is close to the atomic size, right? How you can increase the computing power in the future. That's why maybe you hear about people are discussing about the quantum computing or something. I think that's something I want to discuss here because it's quite interesting about the future development trend. Anyway, I think I need to check if any question. Okay, no question here. Good. Okay. So anyway, I think this is the motivation because when you invent the IP address protocol, people think 22 bits are enough, but now definitely could be not enough. Okay, so let's look at the IPv6, the datagram format here. I think it's pretty similar to IPv4. We have definitely we have the source address and destination address, right? And we have the payload data that is an above layer, right? For the UDP or TCP, and you have the version number, you have the different header information. But what's the difference between the IPv4 and IPv6? Oh, so definitely first is a 128-bit IP addresses, right? Because this is a motivation. Is there any other difference here? Okay, so here is another, so hold on a second. I think my chat blocked my screen. Oh, it's really hard to change. Hold on a second. Okay, I think that's fine. Okay, so this is a flow label. So it's identified datagrams in the same flow, concept of flow, not well defined here. Okay, so anyway, this is not a very huge difference. I think the difference is compared to the IPv4 is that there is no checksum here because it's to want to speed up the processing of the routers. Okay, but no checksum, they may have some problem. We'll mention later, right? But yeah, just general speaking, it's no checksum here. And I think I want to emphasize the most important difference that there is no fragmentation or reassembly. So still remember when we talk about the routing things, you can segment the datagrams, right? And you can reassemble the datagram. So you need to have some flag here to indicate if this datagram is fragmented or not, still remember, and the fragmentation offset. So you can see here we save a lot of information within the header, right? So you save a lot of information. That means your overhead is low, but also you can speed up the processing speed, right? Because you don't need to decide if this datagram is fragmented or not, right? You don't need to reassemble that. That saves a lot of time, right? That means each datagram here is complete without any further reassembling, okay? So I think this is a most important difference I want to mention here. And then the next question is that how we can make the IPv4 and the IPv6 compatible with each other, right? When you upgrade something, you must think about, okay, so if I have some device without upgrade, how should I deal with that not upgraded devices with the new protocol, right? And people always need to think about that because when you invented the IPv4, you didn't know that, right? We will have a new version. And when you will have a new version IPv6, how you make them compatible with each other? That's an important question, right? So that introduce, okay, anyway, before I introduce how can we make them compatible, here is a quick notation for the IPv6. You can see here the IPv6 addresses are 128-bit addresses represented in hex digits. Okay, so each hex digit is for 4 bits, right? So you can see here, if we have the 4 hex digits, it represents for the 16 bits, okay? And we will have the 8 16 bits, so totally 128 bits. Okay, so that's the IPv4 format. I mean, at least after you learn this class, when people give you a IPv4 address, IPv6 address, you can tell them, right? So you can know, okay, this is a 1 2 3 4 5 6 8. This is 8. I mean, segments, right? Each segment is for the 16 bits. And even it's a 4 digits, but I mean, it's a 4 hex digits, okay? So it's separated by the columns, right? So this is a notation for the IPv6. No question here, right? So this is straightforward, I think. Okay, then the question, as I mentioned, how we can make the translation from IPv4 to IPv6 and how we make them compatible. That's an important question. The reason, just as I mentioned, not all routers have been upgraded simultaneously, right? You cannot assume that every device has been upgraded to IPv6, right? If you send the IPv4, still using the IPv4 with the old devices routers, how you can deal with that, right? So the internet devices have been operated with a mixed IPv4 and IPv6 routers. So the idea is that can we do some translation, right? Can we do some tunneling? So IPv6 datagrams carried as a payload in IPv4 datagram among the IPv4 routers. Actually, I think I can use a simple picture, a simple diagram to let you know. I think the idea is that let's wrap up IPv6 datagram within the IPv4 datagram. Okay, it's like it's in the same layer. Okay, but it's similar to the different layer, right? For example, here, even for the IPv4 datagram, when we talk about that, we know there is a payload area, especially for the UDP and TCP, right? So we can do same thing to the IPv6. We can think about IPv4, between IPv4 and UDP, TCP data, there is another layer, but this layer actually is a virtual layer, right? It's not a physical layer. That's actually it's between the IPv4 datagram and the traditional UDP and TCP payload. You can think about IPv4, as I mentioned, IPv4 has more overhead, right? You have a lot of information, blah, blah, blah here. And IPv6 actually is a slightly less heavy, right? So you can put the IPv6 datagram within the IPv4 datagram, and within IPv6 datagram, you put the actual UDP and TCP data here, right? So I wrap up IPv6 into the IPv4. So that's the idea. And let's see how people actually, I mean, this is just the scheme, right? But in the real world, how the router will be encapsulate that or decapsulate that, right? So how would that happen? That's a question. But this is just a general idea. So let's see how the tunneling and the encapsulation happen. How would that actually happen between the several routers? Okay, let's assume that we have, okay, everything if it's IPv6, that should be fine. Okay, I'm having all of the devices, routers as IPv6. I sent everything in the IPv6 format. There will be no problem. But, okay, so if there is something between B and E, some routers are IPv6 routers. Oh, sorry, IPv4 routers. How should we do? That's the question, right? So even if you can guarantee your institution, your company, your home are using the IPv6, but you cannot guarantee the other routers are in the IPv6, right? So that's the question. If we have something between B and E are not IPv6, how we can use the encapsulated datagrams in the IPv4 format to make it happen. Okay, so yeah, this is what I exactly meant. There is some IPv4 network between the two IPv6 routers, okay? So the idea is that we can use the IPv4 tunneling. So how would that happen? I think the idea is that when you send the IPv6 from B to our site, and the datagram has been encapsulated with the IPv4 datagram, and then this IPv4 datagram can be propagated within these tunnels, right? Within these IPv4 routers. After arrive at the IPv6, you just decapsulate that and take out of the IPv6 datagram and propagate along the IPv6 routers. I think the idea is just very similar to the different layer encapsulate and decapsulate, right? So you just have another function to wrap up IPv6 to IPv4 and use IPv4 to propagate, and then just take out of the IPv6 and then to do the next communication or I mean the message propagation, right? Is there any question here? I will show a more detailed figure, but the high level idea is this. Okay, you have something translate, right? We previously mentioned the IP address translation. Here is like IPv4 and IPv6 format, or just like a format translation, right? You wrap up and translate that and propagate and send and receive and decapsulate and then do another IPv4 or IPv6 propagation. Okay, so here is tunneling with more details. Okay, so from the logic view here, you can see here, you cannot see any IPv4. You just think about, just as I mentioned, from high level, right? You just think about you after the B router, everything is wrapped up in the V4, right? You just connect the using the IPv4 tunnel and send the datagrams and then to the next destination E. But from the physical view, okay, actually we have some IPv4 here, routers here, okay? And this IPv6 and 4 need to play an important role before before itself send the datagram to the next destination CD, right? So let's see some detail here. Okay, if I have a datagram, I've in IPv6 from A to B, no problem, right? No problem, because that's a IPv6 to IPv6. Datagrams also in the IPv6, everything is fine. Okay, and then let's go if, okay, that's why I mean here is an important step. If I send from B to C, that's from V6 to V4. Okay, the source the source is B, the destination is E, and this is the data, right? You need to, just as I mentioned, you need to wrap up things within the IPv4, right? So you can see here, actually the message should be sent from A to F, but after you encapsulate the, I think here is the important thing. Okay, you can see here, the source is changed to B, and the destination is changed to E. Why this would happen? I think here is one important thing, because if I ask you to plot this figure, I leave the source and destination router numbers here and ask you to fill it up. You have to, you need to understand here, okay? So from this router to that router, after I encapsulate with IPv4 format, the destination is going to be E, and the source router would be B. Okay, because from here to here, right, those things are the IPv4. So you have to let the IPv4 routers know that, okay, after I got to the destination E, that's my final destination, right, for the IPv4. Right, that's understandable, right? Because the IPv4 only go through here to here. So the destination would be E, the starting point would be B, right? So the point here is you need to exactly describe what's the travel for IPv4 and IPv6. For the IPv6, actually it's from A to F, no problem, right? But for IPv4, it's just from B to E. Okay, any question here? Okay, now if no, I assume that it's clear. Okay, how do the routers know what version of the router? How do the routers know what version the routers beyond the next one are? Oh, hold on a second. I think another issue pop up. Okay. So, okay, your point is that how does the router knows from B to C, the next router would be C, right? So the B needs to translate that. Is that your point, right? So I think, yeah, that's a good question. So once from B to C, let me double check. Follow-up question is, so B knows C, but how does it know D is the IPv4? how does you mean how does B know D is IPv4? I don't think B needs to know the D is IPv4. He only needs to know what is the last router to be the IPv4 to IPv6, right? So that's what we mentioned previously. You need to have a global routing algorithm, right? The routing algorithm would handle, for example, as I mentioned, if we have the software-defined network, the software-defined network as a central part will control the flow, how the flow will uh, propagate along the network, right? So you need to have a global view, right? So B will not know D is the last thing, but he definitely knows that before E, there is some router is the last router for IPv4, and the E is the first IPv6 back in the path. Does it make sense? You have to have some global information. Okay, so let's see if the question. Okay, yes. So yeah, so from B to E, definitely the router knows that because it has the global switching, global for routing algorithm here. Okay, and then let's continue from B, C to D. Yeah, it's exactly the same, right? From the B to E, just propagate. And then from the D to E, yeah, it's just another propagation. That's fine. And from E, this datagram needs to be decapsulated back to the blue part, right? Okay, and then decapsulate and then just propagate. Okay, so you can note here the source and the destination addresses here need to be careful, right? But if you think about the IPv4 and IPv6 as a two layers, that's fine, right? It's just another layer of the capsulation and the decapsulation. So I think about 20% of the clients in the Google access our services through the IPv6, right? So the Google can do a statistical survey, right? How many users or how many clients access the service through the IPv6 or IPv4. So you can think about that almost 30% of the clients now using the service through the IPv6. And the NIST reports that 1/3 of the all US government domains are IPv6 acceptable. Okay, are capable. Okay, capable. So that's a good thing. And you can see the IPv6 increasing every year based on the Google statistical survey here. Okay. So long time for deployment user IPv6, 25 years and accounting, right? A lot of time. Think of application level change in last 25 years, right? Social media, streaming media, gaming, telesense. So you can think about that. We have been doing the IPv4 for IPv6 for a long time, right? But still not make it everywhere, right? So and any guess, but I think yeah, this is a because I think IPv4 is still capable in a lot of places, right? We are not running out of the IPv4, and for some budget or for some design perspective, if you want to change to IPv6, you have to change a lot of routers, right? You have to change a lot of devices. So yeah, so that's why people, yeah, some companies, some organization want to change that because it's a fast speed, but in some area or some organization, still IPv4 is very popular, right? So you have to that's a translation or decapsulation. Capsulation is very important. Okay. So I think that's what I want to cover today, because for the next lecture, let's finish everything for the software defined network, and we can do that next lecture, considering not all the students here let's just stop with the IP address this section. Any question here? Yeah, so next week we will finish the other parts. Okay. So any question for the IP addresses part? IPv4, IPv6. I think I should describe this clearly. Okay, and I don't know if you want the TA to have a class next week for assignment 3 to have some demonstration or explanation. If you are think that's necessary, I can do that. But if you think just upload the sample answers and you can follow the sample answers to understand how to do that, I think that's fine. That can save us some time to continue the lecture. But anyway, if you think that's necessary, you can send me an email. Okay, I can see how many students would like to request a TA to do a demonstration. But if you think that's fine, yeah, I'm fine. Okay, so if no question, I think today let's end up here, and hope everyone have a nice weekend. Okay. Okay, thank you everyone. Have a good weekend. Bye.